Okay, so this is going to be our first of two discussions in our gas laws unit. And the way this unit is structured is that I'm going to start with the sort of conceptual understandings of gas laws and talk about the theory of kinetic molecular theory and all the factors that affect pressure. And then in the second topic, we're going to talk about how this is applied mathematically. So you're going to do a lot of math with it. All right, so to start, I want you to think about two warm-up questions. And I just want you to think about these right now, and then at the end of this discussion, we'll go back and address these based on what we've learned. So if you threw an aerosol can into the fire, what's going to happen? And try to explain your prediction in terms of pressure and temperature. And a rigid container holds 1 mole of gas. If 3 more moles of gas are put into the container, what is going to happen to the pressure and why? So think about those two questions and jot down your answers. All right, so let's talk about kinetic molecular theory. What does gas motion look like to you? So you're sitting in your house, you can act this out. If you are acting it out, I imagine you're moving your hands around really quickly and rapidly. That's what most people do. And that's, pretty accurate actually. We use something called kinetic molecular theory, which is just a series of principles that explains the behavior of gas particles in motion. Okay, so the first principle is that these gas particles are really small compared to the container that they're in, and that also means they're far away from each other. So what we're assuming is that they're not interacting with each other. There's no intermolecular forces. Now, that's not a perfect assumption. The more polar a gas molecule is, the more likely it is to interact with other gas molecules, but we're going to assume this. And we're also going to assume that gases are in constant random motion, that they're moving in straight lines with elastic collisions, which means no energy loss. Again, not a perfect assumption, but we're going to make it. And we're also going to assume that at a given temperature, all gases have the same kinetic energy. Now, when we talk about pressure, generally speaking, not necessarily just specific to gases, pressure is a measure of force per unit area. So imagine walking across wet grass, okay? If the ground is really muddy and you were picking your shoes and you could choose between sneakers and high heels, which one would you pick? Well, you'd probably pick sneakers, not only because you might not want to get high heels dirty, but also because high heels are going to sink into the wet ground. And the reason is you have the same weight regardless of what shoes you're wearing, but when you wear high heels, you're exerting that force across a smaller area. So you're actually increasing the pressure, which is going to make you sink down into the grass. If you wore sneakers, or better yet, something like snowshoes, and you increase the area, you're going to decrease the pressure, so you're not going to sink into the ground. Now, when we talk about gases, they exert pressure by colliding with the walls of the container that they're in. Air or atmospheric pressure is the sum of all the pressures of all of the gases in air, and this is exerted in all directions. So air pressure is being exerted on you right now and everything around you, and we don't even feel it because it matches the pressure inside our bodies. But if you've ever driven up a mountain or something like that and you felt your ears pop, that's the pressure inside equalizing with the change in atmospheric pressure outside. Now, when we measure pressure, we can use different instruments. And the most common is a barometer. There's a bunch of different units you can use to measure pressure as well. The sort of comparison point we use is pressure at sea level, which is defined as 1 atmosphere. And that's equal to all these other units here. So 1 atmosphere is equal to 760 millimeters of mercury, or 760 torr, or 101.3 kilopascals. Now I'll tell you, we rarely, if ever, use torr in this class. You don't need to know that, but you should know the conversions to millimeters of mercury and kilopascals. Okay, so let's look at an example. If I wanted to convert 227.4 kilopascals to atmospheres, the easiest way from my perspective is to use dimensional analysis, but I'm not going to force you to. And so you would divide the kilopascals by 101.3 to get atmospheres. Now let's think about factors that could cause a change in pressure. Remember, pressure is force per unit area, so I'm going to have to change one of those things. And there's really 3 factors that can cause a change: a volume change, a temperature change, or a change in the number of moles of gas. So let's address each of those one by one. All right, so first let's talk about temperature. So let's think about what happens as temperature increases. So if you imagine your molecules in a container, and here when we talk about pressure and temperature, we're going to assume that volume is staying constant. So think about the molecules in your container. As temperature increases, the molecules are going to start moving faster. So what are they going to do? They're going to collide more. So that means that the pressure is going to increase. Okay? More collisions with the walls of the container because the molecules are moving faster. So imagine if we were in our classroom and I blindfolded you all and you moved around the room, would you collide more if you were walking or running? Presumably running, because you'd be moving really, really quickly, and that would just lead to more collisions, both with the walls of the container and with each other. So likewise, if the temperature decreases, the pressure is going to decrease. And that's because there are fewer collisions because the molecules are moving more slowly. So would you collide more if you were walking or if you were crawling? Walking, presumably. So that means that pressure and temperature have a direct relationship. As one increases, the other increases, and vice versa. One decreases, the other decreases. And so if we were to sketch a graph of that, it would look like this. All right, so let's talk about pressure and the number of moles. As the number of moles increase, the pressure increases as well. And this is because we just have more molecules in the container, so there's going to be more collisions. Okay, if another class of students came over to our classroom and we were all running around, would we collide more or less? Well, more, because there's more people. Similarly, if the moles decrease, the pressure decreases, and that's because there are fewer collisions, right? Fewer molecules in the same space. If half the class left, we would collide less. So pressure and number of moles, again, have a direct relationship. As moles increase, pressure increases as well. Okay? All right, so let's talk about pressure and volume. Now, let's talk about when volume decreases. So for this, I think it's really helpful to imagine squeezing a balloon, okay, to decrease its volume. As I squeeze the balloon, what's going to happen to the pressure? It's going to increase, okay? And that's because I've created a situation where there's much less space to move around. So there's going to be more collisions with the walls. So imagine if our entire class went into a tiny little room, we'd collide way, way more because there's less space for us to move around, okay? And eventually you'd exert enough, there'd be enough pressure in the balloon that it would pop. And now if the volume increases, the pressure will decrease. So there will be fewer collisions with the walls of the container because there's more space to move around. So imagine if we all went into the gym to run around, we would collide much less, right? Because there's just more space for us to move. So pressure and volume have an inverse relationship. Now, when you sketch a graph of an inverse relationship, be very careful. It looks like this. This is really y equals 1 over x, not y equals negative x. So it's inverse rather than indirect, okay? So let's also talk about the relationship between volume and temperature. So we've talked about the 3 factors that affect pressure, but volume and temperature can have their own relationship when pressure is held constant. So what is this relationship? Now, the easiest way to think about this is to imagine the behavior of a balloon if you heated it up or left it in a cold place, like left it in a garage overnight, okay? So as temperature increases, the volume is going to increase as well. So let's think about why this is. So pressure wants to equalize. Well, pressure doesn't want anything. It doesn't have a brain, but pressure equalizes itself, okay? So a balloon is going to expand or contract to try to keep the pressure inside the balloon the same as the pressure outside the balloon, so the same as atmospheric pressure. So if I increase the temperature, that's going to make the molecules start to move faster and faster. So they're going to collide with the walls of the balloon more. So the balloon is going to expand to try to keep those collisions constant. So this will keep the pressure constant. Now, as temperature then decreases, the volume is going to decrease. And again, this is because we're going to keep the pressure constant. As the molecules start to move more slowly, the volume of the balloon has to decrease in order to keep the collisions constant, so to equalize the pressure inside with the pressure outside. Okay, so by moving the walls of the container in closer, it's going to maintain the same level of collisions that there was before. All right, so let's look back at this warm-up question. An aerosol can is thrown into the fire. What's going to happen to the can? So let's think about this. The can is going to explode. All right, the molecules are going to move faster and faster and faster, and fire is, as you know, quite hot. And the pressure is going to increase and increase and increase, and the pressure inside the can is going to try to equalize with atmospheric pressure. Eventually, the can won't be able to withstand that pressure, and so it's going to explode to equalize the pressure. If a rigid container holds 1 mole of gas and 3 more moles of gas are put into the container, what's going to happen to the pressure? Well, the pressure is going to increase. There will be more collisions because there's more moles of gas. Okay. All right. So you're going to apply this in a lab and also in some homework. And so think about what questions you might want to ask so we can talk about them.